In the previous video, we studied properties of an image formed by a convex lens. This is a table representing those properties. As you can clearly see from the table, as the position of the object varies, the properties of the image change. Similarly, we will study the properties of an image formed by a concave lens. Do you remember the concave lens? Concave lens is a transparent material which has two spherical surfaces and both of them are curved outwards. We also know that a concave lens is a diverging lens. It's called so because all the rays of light from a point object move away from each other after refraction from the concave lens. I haven't shown the refraction happening inside the lens as that's not required here. Okay, so what are the properties of images formed by a concave lens? Let's make a table just like we did in case of convex lens. The column on the extreme left represents various positions of the object on the principal axis. We will draw ray diagrams for each individual case here as well. First, let's start with this one. When the object is between F1 and O. Consider the top point on it. We will try to find out its image location first. Note that two rays from a point are sufficient to draw its ray diagram. Which two rays should we take? We will take the same two rays for concave lens as we'd taken for the convex lens. First, the incident ray which is passing through the optical center. It will travel in the same direction. What about the other ray? The other ray will get refracted like this. If we extend it backwards, it will go through the principal focus F1. And this point of intersection is where the image is formed. We will join this point with the principal axis to get the entire image. What are the properties that you can identify by just looking at the image? Well, first, it's smaller in size relative to the object. It is formed between F1 and O. It is a virtual and erect image. So this was the case when the position of the object was between F1 and O. Similarly, these will be the ray diagrams that we will get for other few positions of an object. These are all different ray diagrams formed by keeping the object at different positions. The only case we haven't considered here is the object kept at infinity. We will come to it soon. For now, observe these ray diagrams carefully. Notice what happens to the image as the object gets away from the lens. You can see that for any position of the object, the image formed is always smaller, virtual and erect. Also look at the position of the image. It's always formed between F1 and O. No matter how far I move away from the mirror, the image is always between F1 and O. As the properties are similar for the first 5 cases in the table, let's use just 2 columns on the right side of the first column. The image position and the size and the nature of the image. For all the first 5 cases, the image formed will be between F1 and O, and its size will be small, and the nature will be virtual and erect. For all these 5 cases, these properties are common. What about this case when the object is kept infinitely far away from the lens? Well, for an object at infinity, we consider all the rays reaching the lens to be parallel to each other. These rays diverge after refraction as usual. But when I extend these rays backwards, they meet at a single point. And what is this point called? Yes, this point is called the focus. In our case, this is the principal focus. However, this may not always be the case. For instance, when the parallel rays are traveling in this direction, then the rays appear to come from this point, which is a focus but not a principal focus. This image is also virtual and erect. And as it's formed at a single point, it's very small in size. When the object is at infinity, the image is formed at the focus. The image is point-sized and it's virtual and erect. Okay, so these were the properties of an image formed by a concave lens. We will understand the lens formula in the next video.